Okay, so we are going to go through Exam 5 practice. I've updated it. We are going to go through gases, solutions, and acids and bases. Acids and bases will not be on the fifth exam, but I put it in here for practice anyway. So off we go. I'm also going to be doing this real time, so there's going to be stutters as I kind of do the math on my computer here. So, first question. Uh, the unit of one atmosphere used to describe the pressure of a gas is equal to. Okay, so this is just a general idea. Um, one atmosphere, we use atmospheres for the ideal gas law, but we don't need to use it for the combined gas law. One atmosphere is equivalent to 760 millimeters of mercury. That's it. That's the conversion. It's a 1 to 760, and it looks like we have a conversion in the next one, so you're going to see me use this conversion. I should also say you can replace millimeters of mercury with a different unit called torricelli or torr, so 760 torr. Notice that they are the same value, so those units can essentially be interchangeable. So torr or millimeters of mercury, they're interchangeable. So one atmosphere is described as 760 millimeters of mercury. Fantastic. Okay, next one. A tank contains 1.5 atmosphere. What is that in millimeters of mercury? So we are doing a conversion from 1.5 atmosphere to millimeters of mercury. We start with our original number, 1.50 atmospheres times fraction. I want atmospheres to go away, so I'll put it on the top. And I have my little conversion right up here. It's a 1 to 760 ratio. I want millimeters of mercury on the top. One atmosphere is 760 millimeters of mercury. And now I just plug it in. It's pretty straightforward. 1.5 times 760 gives me 1140. And in terms of units, atmospheres cancels, and I am left with mmHg. So 1140, it looks like A is my answer there. All right, good. In response to Boyle's law. So Boyle's law, I don't mention the different types of law, Boyle's law, Charles' law, Avogadro's law, but ultimately none of that really matters. What we're interested in is what is the relationship between the pressure of a gas increasing and the volume decreasing. So what we're looking at is pressure versus volume. Boyle's law is going to be pressure versus volume. Okay. In response to Boyle's law, the pressure of a gas increases. Pressure increases as the we see a decrease in volume, which makes sense. If you compress something and make it smaller, there's more particles moving, hitting the walls more often. That's going to increase the pressure. In response to Boyle's law, the pressure of a gas increasing as the volume decreases because, okay, the kinetic energy of the particles increase. Kinetic energy is based on temperature. That's not true. The kinetic energy of those particles are moving. They're all moving at the same pace. Doesn't matter that I've compressed them, I've made them in a smaller volume. They're still moving at the same volume. The temperature of the gas increases. Nope. Notice there's no mention of temperature here. Temperature is independent of those two. It hasn't been varied at all. There is no change in temperature when you decrease the volume. The gas particles get bigger. There's nothing that would change the size of the gas particles, not to mention the gas particles themselves are they're kind of minuscule in comparison to the amount of volume that takes up, so we don't see bigger gas particles. The gas particles strike the walls of the container with more force. In order to do that, they would need to be moving faster. So that would be a temperature thing. They're not moving faster in order to hit with more force, so we would ignore that. They are moving and hitting it more often, right? If you're hitting it more often, you're creating this larger pressure, and hence E is the correct answer here. Temperature is not changing. All but one of these is based on temperature. And so they're hitting it more often, increasing the pressure. If you can imagine we kept things at the same volume but increased the temperature, that would be true. And also, they would be hitting more often because they're moving faster. So they would have more force and they would be colliding more often, both of which would increase the amount of uh, pressure. Okay. What unit of temperature is used in gas law calculations? I put this in for one reason. The answer for this is in Kelvin. Why? Because it's an absolute scale. You cannot use Celsius. We always never use Fahrenheit. We can never use Celsius. It's always Kelvin because we need the value to be a positive number. We can never have a negative number when we're doing a calculation. Always has to be a positive number for Kelvin. Kind of sends things kind of crazy if you have negative numbers. All right. Next one. A volume of a gas with the volume of a gas with a pressure of 1.2 atmospheres increases from 1 to 4. Okay, so we have two equations, and you're provided these equations. The two equations we have are PV equals nRT and P1V1 over T1 equals P2V2 all over T2. So combined gas law and the ideal gas law on the left. This is ideal. This is combined. We use the combined gas law when we have multiple states, which I do here. I have one volume and I increase the volume. So we see some change. We have two different states of gases. We've made a change. So we are going to be using the combined gas law here. I'm going to do this work below. So I'm going to write out this equation, P1V1 over T1 equals P2V2 over T2. Ooh, there's 2. Good. 1.5 atmospheres. This is a pressure. We're going to call this pressure 1. So a volume of a gas with a pressure of 1.2 atmospheres increases from 1 liter. So that's my first volume to my second volume, 4.0 liters. What is the final pressure? So what we're looking for is P2 and a constant temperature. Well, because I'm at a constant temperature, I can actually just cross those out and ignore those. So the new equation is P1V1 equals P2V2. Fantastic. So we have our pressures, we have our numbers, we can start to plug these things in, and off we go. So my pressure 1 was 1.2 atmospheres. My volume 1 was, I believe, was 1 liter. And my volume 2 was 4 liters. Sometimes it does this. So 1 liters to 4 liters. So volume 1 is 1 liter. Pressure 2 is what I'm looking for. And my new volume is 4 liters. Okay. So I'm going to divide both sides by 4 liters. Liters will cancel on that side, leaving behind P2. Liters cancels here, leaving behind atmospheres, which makes sense because I need it to be a pressure. So 1.2 divided by 4, it's 1/4, which makes sense. 0.3 atmosphere, 2 sig figs, 0.30 atmospheres is what you end up with. So again, 1.2 times 1, enter, divided by 4, enter, and you should have 0.30 atmospheres, 0.30 atmospheres. So our answer is B. All right. Good. Simple, straightforward. When you see a situation where you have a change in temperature, pressure, volume, you're using the combined gas law. So for the next one, a sample of gas, I'm going to divide this just so I know. So it belongs there. Okay. A sample of gas has a volume of 5 liters with a pressure of 1.5 atmospheres. When the pressure of the gas is increased, okay, we've increased the pressure. What is the final volume at a constant temperature? So what we're looking for is the final volume. So what do we have? So I'm going to write these down below. Sometimes it's easier to do that. So here we go. I have a volume 1, it looks like, of 5 liters. An initial pressure 1 of 1.5 atmospheres. I am looking for the new volume. I'll put a question mark there. And I have a pressure 2 of 1240 millimeters of mercury. Okay. So again, we are in the same situation where I'm going to be at a constant temperature, so we can just get rid of that. So the equation is just simply P1 V1 equals P2 V2, because we've gotten rid of the denominator because there is no temperature involved. All right. So I'm seeing a problem already. My answer is going to mimic liters, so we expect our answer to be in liters, which is fine. It's what we're looking for. The problem is I have atmospheres and I have millimeters of mercury. I have two different units for my pressure, which is a bad thing. We can't do that. We're not allowed to do that. So what we're going to do is we have to convert one of those. Either I can convert pressure to atmospheres. I can go from millimeters to atmospheres, or I can go the other way around, but they have to match, and it's fine. We can use either one. This is not like temperature. It doesn't need to be in Kelvin. So in order to do that, I will do this because this is the other conversion that we would have done above. So 1240 millimeters of mercury times fraction. I want millimeters of mercury to go away, and I want atmospheres to remain. And remember from that question above, one atmosphere was equivalent to 760 millimeters of mercury. MMHG cancels and leaves behind atmospheres. If I do the math, so this is going to be 1240 divided by 760, giving me 1 point. We got 1.63, well, 366, technically 1.63 atmospheres. And now we are ready to go. Now I can plug my numbers in. Pressure 1 is 1.5 atmospheres. Volume 1 was 5 liters. Equals, I'm looking for the new, oh, no, I have pressure 2. Pressure 2 was 1.63 atmospheres. And the new volume is what we're looking for. So I'm going to divide both sides by 1.63 atmospheres, V2, and divide both sides by the same thing. Can't change that. Atmospheres. We're going to see that atmospheres cancels, leaving behind liters. So now I do the math. 1.5 times 5, enter, divided by 1.63, enter, and we have a number. So pressure has increased, so that means volume should decrease. We should have a number that decreases the volume, which makes sense because more pressure equals less volume. And so you end up with 4.60 liters, which makes sense. It's less. 4.6 liters is what we end up with. So our answer here is B. Great. Moving on. Again, that combined gas law, we're seeing changes in temperature or pressure or something like that. All right, moving on to this next one. These are conceptual. So a balloon is filled with helium gas. The gas type will not matter, okay? For the following question, select the letter balloon diagram that corresponds to the following. So what we're seeing here, the initial volume, A seems to have decreased in volume. B seems to be a steady, no change in volume, and C seems to increase in volume. So these are all related to the volume question of what's going to happen, increase, decrease, or remain the same. So a balloon is put into a chamber whose pressure is less than the atmospheric pressure and at atmospheric temperature. Okay, so what I'm seeing here seems a little more complicated than it needs to. At atmospheric temperature. So temperature is not changing again. So we don't have to worry about temperature at all. So what has happened is it's put into his pressure. Pressure is less than atmospheric pressure. So the initial one seems to be at the pressure of the atmosphere. And then what happens, so that's P1 is atmospheric pressure. And then we see a decrease in pressure. So we're going to see a decrease in pressure. That is going to lead to what? An increase in volume, right? So as I decrease pressure, volume increases. We can also look at this another way. We can look at it P1 V1 over T1 equals P2 V2 over T2. Temperature is, like I said, it's constant. And what we're going to see is if I had a pressure of 1 and then I shifted in a volume of 5 liters, and I shifted it to a pressure of 0.5, what's going to happen to the volume? So you can just plug numbers in if you want to, but I do know that if I decrease pressure, volume is expected to increase. So in fact, I should just move all this down here. All right. So I do know that if I'm decreasing pressure, I'm expecting volume to increase. The one that has an increased volume seems to be balloon C. So we're going to say balloon C in that case. All right, perfect. Next up, the temperature is changed from 50 to -50 at constant pressure. So we're ignoring pressure this time. So if temperature decreases, what happens to the volume? Well, if you cool a balloon down, what's going to happen is you're going to see also a decrease in volume. We would expect this to be balloon A. Balloon A it is. Okay, so it's just kind of looking at the interactions between volume and temperature and whatnot. And there we go. All right, next up. At constant temperature, okay, so no temperature change. The sample of helium is at 760 torr, again, millimeters of mercury, same thing. Compressed from 5 to 3 liters. So right away, I'm seeing a change in volume. This means that I am again using the combined gas law for this. So P1 V1 over T1 equals P2 V2 all over T2. Kind of gave myself no room for this. I'll do it above. In a closed container, it was compressed. Okay, so what is the new pressure exerted by the helium in its container? Okay, off we go. So I want my answer in torr. We don't need to change the pressure. It does not need to be in atmospheres. The only thing that always needs to be converted is temperature, which has to be in Kelvin. All right, so pressure 1. Is there any mention of pressure? Oh, yeah, so we do want the new pressure at a constant temperature. So again, we can ignore temperature, and it's P1 times V1 equals P2 times V2. So off we go. We're going to plug numbers in. Pressure 1 is 760 torr, or millimeters of mercury, same thing. Volume of 5 liters equals P2 times, looks like going to be compressed to 3 liters. Pressure 2 is going to be equal to what? So now we do the math. 760 times 5, enter. All right, 760 times 5, enter, divided by 3, enter, gives me 1,267, or 1,270, as it were. 1,267. 1,200, and so B, this is 1,267 torr, but we're only going to 3 sig figs, which is going to be 1,270. Perfect. That's it. All right. Next one. Complete the following statement. Charles' law. Again, I don't really care, but we're looking at volume as a function of, okay, Charles' law. So I guess technically we're supposed to know what these different ones are. I never teach the names because they don't really mean anything other than, so we did Boyle's law up here. We also did Boyle's law in lab, is pressure versus volume. So Charles' law is not going to be pressure and volume. Yeah, Charles' law is going to be temperature and volume. Okay, so temperature and volume. So we know that volume and pressure is Boyle's law because we saw that in lab. So we can get rid of the first, it's not pressure. Quantity of gas is Avogadro's law. This is going to be Boyle's law. So the question is the volume of a gas and temperature. All right. So if the volume of a gas, so let's just look at the relationship, like ignore the question. If I increase the temperature, we should see an increase in volume. They should be directly related. One goes up, the other one goes up. Okay. So if the volume of a gas increases when actually it looks like decreases when the temperature decreases, the volume of the gas should also decrease. So when the volume of a gas decreases, when the temperature also decreases. So Boyle's law is going to be uh, temperature versus volume. Okay, good. Moving on. So a gas sample in a closed expandable container with initial volume of 5 liters was allowed to warm from 25 to 35 degrees C. What is the new volume? So we're changing volumes. So again, we are going to be using P1V1 over T1 equals P2V2 over T2. We have temperature changes. We have volume is what we're looking for. We can ignore pressure. That seems to not change, so we don't have to worry about pressure. The other thing that we have to look at is we have to recognize that these temperatures are in degrees C. They're not allowed to be in degrees C. So we have to make sure that we convert these into degrees Kelvin. So 25 in degrees Kelvin is 298 K. 35 is 308 K. And now we are ready to just plug these in and solve our problem. So our volume initial was 5 liters with our temperature of 298 Kelvin. We're looking for the new volume. Oh, that pressure canceled. And our temperature of 308 Kelvin. We expect volume to increase because temperature increased. So in order to do this, I can cross multiply 5.00 liters times 308 Kelvin is equal to volume 2 times 298K. Divide both sides by 298K. Divide by 298K. This cancels. I'm left with V2. Now I can do the math. 5 times 308, enter, divided by 298, enter, gives me 5.16 or 5.17 liters. Looks like C is going to be my answer there. Okay, off we go. Last one on this page. See how many more we have. We have a handful more. Okay, so, right. Okay, so the temperature of a 500 milliliter sample increases from 150 to 350. What is the final volume? Okay, so again, we are seeing changes. So this is again going to be P1V1 over T1 equals P2V2 over T2. It looks like volume changes, temperature changes, and pressure is kept constant. So volumes and temperatures, we have volume 1, 500 mils. Temperature 1, 150 and 350, and they're both in Kelvin, so we don't have to do any conversions. So 150 Kelvin equals, we're looking for the new volume when the temperature turns out to be 350 Kelvin. Temperature is going up, so we expect volume to increase as well. And now we do the math. So we can cross multiply, or I can multiply both sides by 350. We'll just keep it simple. 500 milliliters times 350 Kelvin equals 150 Kelvin times V2, divide by 150 Kelvin, divide by 150 Kelvin. Kelvin cancels. I am left with V2 equals 2 milliliters. And now we do the math. These cancel. All right. 500, let's see, 500 times 350, enter, divided by 150, enter. 1167, 1170 B. Feel like I've done this one before, but not really. Okay. All right, good. So 1170. There we go. Math done. Next up, a gas containing 1.5 atmospheres, 320. What will be the gas pressure? okay, again, this is 1.5 atmosphere, 320 Kelvin. What is the new gas pressure at 450 Kelvin? So we just did this, some other version of it. It's another opportunity to do one of these. So I'm going to leave it to you to do this one. We do know that the temperature increased, so the pressure should increase. That means that I can eliminate all of these. In fact, I can eliminate all of them, and it comes down to this. So when the temperature increases, so should the pressure. Our answer is going to be C. Volume, the pressure increases. Oh, I guess this one doesn't have a pressure increase, but actually it doesn't matter. So we can do this calculation. Volume is kept constant. We see an increase in temperature. Pressure is going to increase as well. There's only one option here for actually showing an increase in pressure. All right. A nitrogen gas sample at 500 mils, the pressure of 740 and a temperature of 25. When the new volume, what is the new volume? Okay, so let's highlight the things that we have. 500 mils, 740 torr at 25 degrees Celsius, and we have a change. So those are my volume one, my pressure one, and my temperature one. I'm going to put it up here because we have to convert this into Kelvin. 25 plus 273 is going to give me 298. And now I'm going to highlight in a different color. What is the new volume? So that's going to be my V2. When the temperature was changed to 50 degrees Celsius, okay, so we have a new temperature and a new pressure. This is going to be my pressure 2, and my temperature 2 is going to be what, 273 plus 50, 323 Kelvin. Again, temperature is the only one we need to convert. And so now, it's not a whole lot of room here, but I'm going to plug these into the equation. Nothing is kept constant. So we can't really kind of predict unless they're both going in the same direction, but we don't need to worry about P1 V1 over T1. T1 equals P2 V2 over T2. And so now I'm going to plug in numbers. My pressure one was 740 torr. My volume one was 500 mils. All divided by my temperature one, which was, I think, 25. Yep, 25 degrees Celsius, which is 298. Equals, okay, my new pressure is 760. I am looking for the new volume, right? Yep, I'm looking for the new volume. And my pressure is, or my temperature was 323 Kelvin. And so now we do math. This one seems more complicated. I'm going to do a little bit of cross multiplying. So 740, I'm just going to use the numbers now because I'm kind of out of space, times 500 times 323 equals 760 times V2 times 298. And so I need to divide by 760 and then 298. We can just do them together. So 760 times 298. There we go. V2 equals. So now let's do the math. So 740 times 500, enter, times 323, enter, divided by 760, enter, divided by 298, enter, 527, rounded up, 528 milliliters, because I know torr cancels, I know Kelvin cancels, leaving behind the only unit of milliliters. Okay. So 528, there it is, A is the answer. Good. All right, moving on. What is the volume of 550 grams of N2 at a pressure of 600? Okay, so in this case, it looks like we are now not seeing a change in pressure, temperature, and volume. So we know the equation here is going to be PV equals nRT. So we are going to be using the ideal gas law in this case because I have quantity, mass, I have a pressure, I have a temperature. Notice I do not have multiple, right? So I only have one of these. Okay, so we're going to be using PV equals nRT to solve this. In fact, I'm going to give myself a little bit more room. I'm going to add a page and I'll copy and paste this so we have these problems kind of all on their own. All right. So probably going to highlight. There we go. Copy. Of course, it's going to do that. Let's try this. Paste image. Good enough. There we go. Okay, so let's solve this problem. I know that I'm going to be using PV equals nRT because we have pressure. We have pressure, okay? But we only have one pressure, one temperature, one volume. So we know we need to use the gas law somehow, some way. Okay, so here's the thing that we have to think about. So the R value, R is equal to 0.0821 liters times atmospheres all over moles times Kelvin. I need to make sure that whatever my units are, they match this. So my pressure needs to be in atmospheres. Oh, needs to be in atmospheres. And it's not. I have 650. So my pressure needs to be converted. 650 millimeters of mercury times fraction. I want millimeters of mercury to go away. I want atmospheres to remain. I have to have atmospheres in order to match this. One atmosphere is 760 millimeters of mercury. Millimeters of mercury cancels. And now we are off to 650 divided by 760. Enter gives me 0.855. So 0.855 atmospheres. Great. So we have a pressure. My pressure is 0.855 atmospheres. Next up, volume. Volume is what we're looking for. So I'll leave that as just as V. Next up, moles. Okay, so the quantity is moles. Well, I have 50 grams and I know that it's nitrogen. We can convert that, right? If I asked you to convert 50 grams of nitrogen into moles, you can do that. I know that I start with, so my moles, I have 50 grams of N2 times fraction. I want grams of N2 to go away. I want moles of N2 to remain. 1 mole of nitrogen is 28.02 grams. Where did I get that number? This is all from the periodic table. 1 mole of nitrogen weighs, one nitrogen weighs 14.01, but N2 has 2 nitrogens. Grams of nitrogen cancels, and I have moles of nitrogen to remain. So 50 divided by 28.02 gives me 1.78 moles of nitrogen, 1.78 moles of gas. R, we're going to plug that in, 0.0821 liter atmospheres per mole Kelvin. And then finally, my temperature was 15 degrees Celsius, 15 degrees C plus 273, right? We always have to do that as well. Always has to be in Kelvin, 288 K. We can plug that in, 288 Kelvin. Done. Divide both sides by 0.855 atmospheres. Divide by 0.855 atmospheres. Erase this. And this is what we have. Let's do units. Moles cancels, Kelvin cancels, atmospheres cancels, leaving behind what we would expect for volume, liters. And so now we do math. 1.78 times 0.0821, enter, times 288, enter, divided by 0.855, enter, 49.2 liters. 49.2 liters is going to be my volume. 49.2 looks like it rounded fine. E is going to be my answer for this one. So E is the answer for this. All right. How many moles of oxygen present in a cylinder that contains 25 liters at a temperature of 0 and a pressure of 1 atmosphere? So off we go. So I'm going to copy this now. Copy, I'll paste this below, and we will work on it. Oh, right. Paste as an image. Boom. Off we go. All right. I have a volume. I have a temperature. I have a pressure. Only one. So we're not using the combined gas law. We are using PV equals nRT. I know the pressure of 1 atmosphere. And that matches my units of R, so we're good. I have a volume of 25.0 liters. I am looking for moles, 0.0821 liters times atmospheres all over moles times Kelvin. This one's easier than the other one. My temperature of 0 degrees Celsius is 298 Kelvin because I just add, oh, sorry, not 298, is 273. 273 plus 0 is 273. 273 Kelvin. And I'm moving these two to the other side. So I'm going to divide this side and this side by 0.0821 liter atmospheres per mole. K times 273 Kelvin. Divide both sides by that. So I'm just going to copy and paste it because it's going to make it faster. Done. And off we go. So that would cancel all of this, leaving behind this. Okay, let's do units first. Atmospheres cancels, liters cancels, Kelvin cancels, leaving behind just moles, which makes sense. And now we do the math. So 1 times 25, enter, divided by 0.0821, enter, divided by 273, enter, 1.12 moles of this gas, 1.12 moles. Looks like B is going to be the answer for this one. All right, moving on. How many grams of chlorine gas are present in, okay, 150 liter cylinder at a pressure of 1 atmosphere and 0 degrees Celsius? Okay, so we want a mass, but we know that we are going to be using PV equals nRT somehow, some way. So let's take our problem. Paste, there we go. And off we go. How many grams of chlorine gas are present in a 150 liter cylinder, 1.0 atmospheres, 0 degrees Celsius? We know that this is a gas problem because of the presence of pressure. PV equals nRT. What do we have? Well, I've got pressure. Always know R. I've got volume at 150. I know the temperature. The only thing I don't know is moles. Great. If I can solve for moles and I know it's chlorine gas, which is Cl2, we can figure out how many grams we have when we figure out moles. So this time, instead of giving you grams and asking to solve moles and plug it in, we're working this in a different way. We have pressure, we have volume, we always know R, and we have temperature. The only thing left is for us to get moles. Once we have moles, then we can figure out what mass we have. All right. And the numbers are actually pretty easy, not a whole lot of conversions to do. Pressure is 1 atmosphere. My volume was 150 liters. My moles is what I'm looking for. R is constant, 0.0821. Liters times atmospheres all over moles times Kelvin. Okay, there we go. All times 0 degrees Celsius, which is 273 Kelvin. Again, I'm going to divide by the right-hand side. So all of this is just going to be divided over here. Moles equals. So let's do the calculation. Atmospheres goes away, liters goes away, Kelvin goes away, leaving behind moles. And so now we do the math. So again, 1 times 150, enter, which gives me 150, divided by 0.0821, enter, divided by 273, enter, 6.69 moles. 6.69 moles. And we don't have an answer for this because that's not what we're looking for, is it? All right, so 6.69 moles. There we go. And now we need to take it a step further. I need to get moles of Cl2 because that's what it is to grams of Cl2. 1 mole of Cl2, I know that the mass of Cl is 35.453 times 2, 70.906 moles cancel, leaving behind grams of Cl2. So 70.096 times the moles of 6.69, enter 474. Yep, 474 grams. So we're looking at B for an answer here. So again, sometimes you can just write out the equation and see what information you have and what you don't have and solve it that way. All right, next one. A 1.26 gram sample of helium at a pressure of 1.123 and a volume of 32.6. What is the final temperature of the sample? So I'm going to skip over this one. You are going to solve this one the same way we solved, I believe it was because I was given mass. I am given mass here. So 15 is the same way to solve 18. So I'll leave it at that. The next one, 1 gram sample of an unknown gas has a pressure, a volume, and a temperature. What is the molar mass of the gas? Okay, so it's a little bit more complex, but not really. We are still using PV equals nRT. How do I know? Again, only one state, so PV equals nRT, and I'm given a pressure, and I'm given a temperature, and I'm given a volume. So PV equals nRT will be used. You don't even need to know what to solve for, depending on what we have. It looks like we have mass, but that's going to come later. I know I have a pressure here, so we have pressure. Okay. I have a volume. Yep. And a temperature. So we have temperature, we know R, so we're solving for moles. More importantly is if I look at how we're actually going to solve this, molar mass, and the units are right there, are grams per mole. I do have a 1 gram sample, so I have 1 grams. So if I know the value of moles, I can literally just plug it in here and solve for my molar mass. So we really want to solve for moles, plug it into this molar mass equation, and we can solve it. So my pressure, 35.8 millimeters of mercury. That needs to be converted. So 35.8 millimeters of mercury times fraction. I want millimeters of mercury to go away. 760 millimeters of mercury to 1 atmosphere. Again, we have to match the units of R. So 35.8 divided by 760, 0.0471. So my pressure is 0.0471 atmospheres. My volume is 20 liters. I am looking for moles. My R is fixed as a constant, 0.0821 liter atmospheres per mole. Okay. And my temperature is 25 degrees Celsius, which turns out to be 298 Kelvin. Again, I'm going to divide this side by R and temperature. Atmospheres cancels, liters cancels, Kelvin cancels, leaving behind moles. And now we do the math. 0.0471 times 20, enter, divided by 0.0821, enter, divided by 298, enter, 0.0385. So 0.0385 moles, 0.0385 moles, which I plug in 0.0385 moles. And my molar mass, 1 divided by 0.0385 gives me 25.97. So 25.97. So grams per mole, 25.97. So 26. So we'll call that A. That's it. All right. Next one, the molecular weight of a gas is if 3.5 grams occupy the space of 2.1 liters at standard temperature pressure. Okay, standard temperature pressure. Standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. And off you go. We're going to solve it the same way we solved the previous problem. So both of these, in fact, are going to be solved the same way we did 19. So give those a go. You should get, hopefully, a correct answer for those. Now we move on to the final handful of questions. These are unit conversion, and really these are stoichiometry as well. So last question, I'm going to cover this one. And all right, so a 5-gram sample of aluminum reacts with excess H2. Basically, what we're saying is I don't have to worry about H2SO4. There's plenty there. What volume of H2 gas is produced at standard temperature pressure? Okay, so what I am doing is I know that this is a stoichiometry problem because A, I'm given a balanced chemical equation, but I am converting from aluminum to a different chemical in hydrogen. So I'm going from aluminum, converting to hydrogen gas. Okay. So in order to figure it out, we know that we have what is the volume of H2 produced at standard temperature pressure. So PV equals nRT. We are looking for volume. I know the pressure, standard temperature pressure. I know the temperature, standard temperature pressure. I know R. And do I know moles? So I need volume. Finally, this is really what I'm looking for. I need to solve for moles through stoichiometry, and then I can plug that in and go. So if I have a 5-gram sample of aluminum times fraction, I can never convert from one chemical to another. I can't use molar ratio until I get moles. So I want grams of aluminum to go away. I want moles of aluminum to remain. 1 mole of aluminum, I just need a quick periodic table. 1 mole of aluminum is 26.98 grams. 26.98 grams. Grams of aluminum cancel. Right now, if I stopped, I would have moles of aluminum. But that's not what I want. I want to get rid of moles of aluminum, and I want to end up with moles of hydrogen. So according to the balanced chemical equation, 3 moles of hydrogen is equivalent to 2 moles of solid aluminum. Moles of aluminum cancels, leaving behind moles of H2. And off we go. So 5 divided by 26.98, enter, times 3, enter, divided by 2, enter, 0.278 moles of hydrogen, which now is going to get plugged in over here. So my pressure, we're at standard temperature pressure, is 1 atmosphere. I'll use green for this. My pressure is 1 atmosphere. My volume is what I'm looking for. My moles, we just solved through stoichiometry. My R is a constant, 0.0821 liter atmospheres per mole K. And my temperature is 273 Kelvin or 0 degrees Celsius. I'm going to divide both sides by 1 atmosphere, divide by 1 atmosphere. Volume is equal to what? So 0.278 times 0.0821, enter, times 273, enter, divided by 1 gives me 6.23. All right, last bit. Moles cancels, atmospheres cancels, Kelvin cancels, leaving me with 6.23 liters of gas A. There we go. So, with that said, these two problems here are not at standard temperature pressure, but they can be solved in the same exact way. You're given a mass, you're asked to solve for a volume. All right, so that was the gases section, solutions part to come.